This talk is for people who have heard of Rust. Maybe you've heard it's a safe systems programming language, so it can do the same things that C and C++ can do, but it doesn't have like segfaults, use after free. You've heard that. You think that's interesting. You're curious to know more, but you haven't gotten a chance to sit down and use the language and really see how Rust accomplishes that and what that means for programs written in Rust. You haven't gotten a chance for Rust to really click yet. That's what this talk is going to try to do. And I think for most people, it takes a few weeks to really get comfortable with the language. Rust has a bit of a learning curve, and that's a lot of time. A few weeks is a lot of time, and most people don't have that much time. And so I'm going to really try to compress the key ideas of the language into an hour. And to do that, I'm going to need to make an assumption. I'm going to need to assume that you're comfortable with C++. Now, you don't need to know all C++. I'm not a C++ expert, but if you know what a constructor and a destructor are, that's pretty good. If you know what a move constructor is, that's fabulous. That's all we need. But even if you're more of a C programmer, that's fine. For most of our purposes in this talk, most of the slides, a comparison to C is pretty close. So that's what we're going to do. We're going to look at a lot of side-by-side Rust and C and try to get right to the nitty-gritty details of how does Rust do the safety thing, and what does that mean for us? What I'm going to do is I'm going to record this talk twice. I'm going to do it slow, and then I'm going to do it quickly. And this is the slow version. So you're listening to the slow version. So this video is probably going to be way more than an hour. I think it's going to be more like 2 hours. We're going to see. So if you want to watch a fast, challenging talk, watch the other one first. I'm going to link it. This is going to be a lot slower. And I think 2 hours is probably a little too much for most people. Like 2+ hours, that's a lot of stuff. So you might, if you're on the fence, watch the faster talk, and you can come back to this one as a reference. If there's a slide that doesn't make sense or you want to hear more about a particular point, click back to the slow talk and just look at that point. You can use it that way. Or if you're really interested in a long, slow, really detailed talk for 2 hours, watch this one. That's cool too. So I'm recording this one first. I'll do the fast one next, and I'll make sure they both link to each other. So let's get started. So yes, Rust is a big language. It does have a bit of a learning curve. There's a lot to go over, and there's no way that I could possibly compress enough Rust into an hour that you could actually write real Rust programs after an hour. That's not reasonable. I'm really going to try to focus on just the key ideas, and we're going to use those side-by-side comparisons to skip over as much as possible, to just get to those ideas. So the big thing is syntax. We're mostly not going to talk about syntax. A lot of Rust syntax looks like C++. A lot of things will be familiar, but we're mostly just going to glide over it. Critical things like how does Rust handle errors, right? We're not even going to talk about that, And these things in the first list on top, the idea here is they're either maybe a little bit familiar by comparison to other languages. For example, Rust errors and Go errors are kind of in the same ballpark. Their values. The languages both have panics for errors that aren't generally recoverable. Kind of in the same ballpark. Or Rust generics and C++ generics, pretty similar at first glance. You'll recognize functions that are parametric on T, right? So you can pick that stuff up as you go. It won't be too surprising. And we're gonna instead jump to the parts that are maybe the most surprising or the most difficult to pick up as you go. The way that Rust treats references, mutable aliasing, and move semantics. So we're gonna have 3 big ideas about those 3 things. That's what we're gonna focus on, and the rest. When you decide to sit down and really learn the language, you can pick those things up. You can read the book and it'll go over everything in detail. But for now, we're going to focus on 3 big ideas. That's what I want our takeaways to be. So I promise we'll get out of the wordy slides next. This is the last wordy slide for a while, but already, 2 of the 3 big ideas right here. So let's talk about this. Let's get ready to see these ideas. So on top, first, we got some familiar stuff. you know, and then the two big ideas, those are going to be new. So let's talk about the familiar stuff. You know, like C, Rust has two kind of types of pointers, you know, the most commonly, right? You've got what C would call a const and non-const. In Rust, we call those shared references and mutable references. And we call them references, but they work like pointers. You know, if you want to create one, you use the ampersand. If you want to dereference one, you use the star. And we're going to see that. And like const pointers, a shared reference, you're not generally allowed to mutate something through a shared reference. Whereas a mutable reference, you know, if you have a mutable reference to a struct, you can mutate it, assign to its fields, whatever. And this is important, you know, like C++, like C, these references, they're just pointers. So there's no garbage collector. It's not like taking a pointer to something magically keeps that thing alive. No, they're just pointers. And so when we take pointers to things, we have to worry about how long those things live, you know, and in C and C++, if you keep a pointer longer than the object is alive, that's a use after free. But our first big idea in Rust is that we're never going to have a use after free. Yeah, there's no such thing as dangling pointers. When you have a reference to an object, that reference is always valid. And what Rust is going to do is it's going to prove at compile time that we haven't kept any references, any pointers, longer than we should. So if we try to write some code that creates a dangling pointer to something that's gone out of scope, that code's not going to compile. That's going to be one of the first things we see here. That code's not going to compile. So we're going to prove statically at compile time that we're not making any of those mistakes. That's the first big idea. So your references are always valid. You're never going to have a dangling pointer or a null pointer for that matter. You're always going to have references to valid objects that have not been destroyed. Big idea number 2, no mutable aliasing. Mutable references are unique. So we could also call mutable references unique references. Sometimes people use both terms. So the idea is if I want to take multiple shared references to the same value, to the same integer, that's fine. You know, multiple const, you know, pointers to the same integer, that's totally fine. But if I want to take a mutable reference to that integer, a non-const pointer, that reference has to be totally unique. There cannot be any other references to that value, either shared or mutable. It has to be the only one. No mutable aliasing. So that's a big deal. So we're going to talk about big idea number 1 first. That's going to be the next few slides. And after that, we'll see some slides about mutable aliasing. Big idea number 2. Let's get started. Number 1. So here's some C++ and some Rust. This is what most of this talk is going to look like, these side-by-side examples. So these two examples are doing exactly the same thing. Let's look at C++ first. So we're creating an int whose value is 5. The curly braces mean that it's in a limited scope, so that int is going to go out of scope at the close curly. We create myIntPutter, point it to the int, but what do? We stash that putter, we keep that putter in a variable that lives longer. So the myIntPutter variable is declared outside the curlies. That means it's going to live after the end of that block. So when we try to print it to see out, dereference that pointer and print it to see out, that's a dangling pointer, right? So this integer has gone away and we're trying to use a pointer to it. It's a classic C++ mistake, right? This is going to be very familiar to most people. And of course, I'll just skip ahead real quick. In C++, it will often do something, but if you run your code under asan, the address sanitizer, you know, it will tell you, hey, you can't do that, right? Like this thing has been destroyed. You know, who knows what it's going to print? This is we call stack use after scope. It's kind of like use after free. Definitely not allowed. Super common mistake for beginner C and C++ programmers, right? For example, returning an array in C. Classic mistake because that's allocated on the stack. You've returned a pointer. You know, classic mistake. The use after end of scope, a destroyed value, dangling pointer, right? Let's look at the Rust. Yeah, in most of this talk, I'm going to try to, again, like I said, I'm going to try to kind of ignore syntax. You know, our goal is not to learn all the punctuation. Our goal is to mostly skip over that. But just in this one slide, you know, we can clarify a few things and kind of get comfortable with the syntax. I mean, we can see, you know, the curlies are curlies. It's very familiar. We declare variables and assign them with equals. So a lot of things are going to be very familiar. dbg exclamation point. That exclamation point means it's a macro. We're not going to talk much about macros. I'm going to mostly use them for printing and a little bit for asserting, but that's it. We're not going to use macros in any fancy way. So dbg, that's a debug print. It's just a print. Taking a pointer, when we create myIntPutter and make it a pointer to myInt, it's exactly the same syntax as in C++ on the left, right? The ampersand means take a pointer, super familiar. We can see that we use let to declare variables. That's just creating a variable. Typically, the type of variables is automatically inferred. So here, the types go on the right. You can see, let myInt :i32. That means it's myInt is a 32-bit int. That type is optional. I think all of the explicit types in my slides will be optional. So when I include them, like I'm doing here, it's just for clarity, just so we can, if it's a type we haven't seen before, I'll try to include it. And we can see that the pointer to int, ref i32, that's different syntax. So in C++, we'd say const int star, and here we say ref i32. But it's exactly the same thing. It's a pointer. And let's see what Rust does with this. So here, this code's doing exactly the same thing in C++. This code doesn't compile. And that's going to be a big theme. We're going to look at a lot of things that don't compile in Rust. So here, what's the problem? myInt does not live long enough. So Rust kind of knows what's up here, right? What's the next thing it says? Borrowed value, let's see if I can use my mouse. Borrowed value does not live long enough. Right, so Rust knows that myIntPutter is what we call borrowing, taking a pointer to myInt. It knows that myInt doesn't live very long, and we're trying to use that pointer in a longer lived scope. It totally sees what's up, doesn't compile this code. So let's move on to a similar but more interesting example of the same. So string view. This is a C++ 17 type. So that means that not everyone gets a chance to use these modern types, but string view is great. So what is string view? It's like a char star, it's like a pointer to some characters, but it doesn't rely on the null terminator. Instead, the string view kind of knows how many characters there are. So it's actually two things. It's a pointer and it's an integer size, length. So it's a view into a string. And it could be a view into a whole string, or actually it could be a view into one word or one sentence or something, some subset of a string. And the fact that it doesn't need the null terminator at the end of the view is why it can do that. It's a great type. It's like a nicer pointer into strings. That's string view. And one of the convenient things about C++ string view is that you can implicitly convert a string into a string view. So here we say string view, my string view equals, and we assign a string to that. So that's going to implicitly convert the string we assign into the string view. So if you have a function that wants to take a string view as an argument, I can call it with a string and it'll just do the right thing. So that's pretty cool. String view is very convenient. But as we're going to see, it can be a little dangerous because it's a pointer, right? String view is it doesn't own the characters. It doesn't keep them alive. It acts like a pointer, and that can cause trouble. So what happens here? So we create my string. It's a heap allocated string. And then we create my string view, but we don't have it point to my string. Instead, we're going to add z, right? So what's that going to do? So my string plus z is going to create a temporary string. So it's going to create a new string allocated on the heap. It's going to have the whole alphabet, right? The original myString characters plus that z in this temporary string. And then that gets assigned to myString view, which means it gets implicitly converted into a string view, which a pointer is taken to that string on the heap. But that string on the heap was temporary, and so it immediately gets destroyed. So myString view is sort of immediately dangling here. And when you try to print it, that's a use after free, and we can see that with asan. So when we run this program under address sanitizer, it tells us, hey, heap use after free right there. You can't do that. Common mistake with string view, and that the fact that you get these implicit conversions to pointers, to borrowing views, is what makes it a little tricky. And some people say don't use string views for local variables, right? This sort of thing can happen very easily, so you'd have to be careful. So let's look at the Rust code. I'm not going to talk too much about the exact difference between capital S string and refstir. other than to say that it's these two pieces they're doing the same thing. This is doing the same things on the left. So capital S string is like a standard string. It's going to be a heap allocated thing. Ref stir, that's like a string view. It's going to point into the string and it's going to know how long it is. So these types on the left and on the right are very, very similar. We can see on the right that the conversion from string constant, which is actually also a ref stir, to string, that's explicit. The conversion back to ref stir with as stir, that's also explicit. It's not implicit here, but it's doing the same thing. It's doing exactly the same thing. We're trying to print it. And like the previous example, this is a compile error, compile time error in Rust. So here the error is very nice, right? What does it say? Temporary value is freed at the end of the statement. Yes, that's true in both C++ and in Rust. The Rust compiler knows exactly what's up. This is a great error. This is one of the errors I think people have been putting in a lot of work to make Rust errors better over the years, and I think this is a great error. So to all the people who work on Rust compiler errors, thank you. Let's make this example. We're going to keep running with string views. Let's make it more interesting. So here we have the same problem, but instead of converting to string view by assignment to a variable, we're going to convert it by insertion into a container. So here I'm pushing back my string into a vector of string views, right? So this is going to implicitly convert my string into a string view again, and the vector lives longer than my string. So this is going to be a use after free in exactly the same way, not by variable assignment, but by using a container. Let's hop ahead real quick to see that. Sort of the same issue, though one thing we might notice, it's an interesting address sanitizer error. One thing we might notice here, stack use after scope, not heap use after free. This is an interesting kind of sidebar. What we see here is that the C++ standard string uses what's called a small string optimization. So because hello world is pretty short, the characters of that string can fit in the space that would normally be used for like the capacity, the heap allocation. They can just write the characters in line there in the string structure on the stack. So this my string, it gets pushed back and cast into a string view. That string view is actually pointing to the stack space that the my string variable occupies. So it's interesting. It ends up being the same problem. Address sanitizer is going to yell at us one way or another, but it's sort of, we get a little debugger's view into how string works here. That's actually going to come up a bit in some future slides. So keep that in the back of your head, the small string optimization. But for our purposes here, it's the same problem, right? We're trying to keep a pointer to something that's been destroyed. In Rust, we're doing the same thing. Here, the conversion from a pointer to a string to that ref stir type, which is like the string view. Here it is actually implicit. It's what Rust calls a deref coercion. Details of that don't matter too much. It's doing the same thing as on the left, right? We've got a vector of these string views, these ref stirs, pushing into it. And true to form, this is going to be a compiler error. So borrowed value does not live long enough. So this is kind of the same thing we saw with the int, right? So Rust knows that the ref stir borrows the string it came from, and it knows that pushing into my vector is like retaining that borrow. So it can see that when we try to print my vector, we debug print it, that it's using this pointer to a thing that's been destroyed. It knows what's happening here. It can follow the fact that we go into a container. It can still track those lifetimes, right? Let's make it a little more interesting. So here, same as before. So we got a vector, we got some string views. So all I've changed is I've added a little helper function. So I've moved pushback into my pushback, right? This little helper. So on the C++ side of things, this really doesn't change anything at all. It really doesn't change anything at all. So if I look here at the address sanitizer result, same issue, right? No difference at all. There's really no difference in behavior here. The optimizer probably inlines this function anyway. No difference, right? It's just a helper function that's doing the same thing. In Rust, it's still not going to compile, so that's kind of like being no different. But what we'll see is this has a big effect on the error that we see. And this becomes an interesting way to start to understand how Rust is doing all this tracking. What is Rust's view of these lifetimes? So here what we see is that the main thing to notice here is the error that Rust is going to give us. It's a little different, and it's happening in my pushback, right? This function is what Rust doesn't like. So Rust looks at main and doesn't have a problem here. Rust thinks this line is totally fine. What upsets Rust is this function. And the important thing to know here to understand why Rust will do this is that when Rust is doing lifetime analysis, it's going to do that function by function. So it's not going to look at how each function is used in all of its callers, or, it doesn't necessarily care about what every function does on the inside. What it's going to do is it's just going to look at each function in isolation. It's going to look at its function signature, and it's going to look at the signatures of the functions that it calls. So this is a very local view. And it's going to say, what you're doing with these values, these objects, these arguments, it needs to always be safe, right? Based on the demands that you've made in your signature need to be enough to prove that what you're doing is always safe. So what's happening here? So we're putting S into V, right? We're going to try to push this string view refstir into a vector of string views. And is that safe, right? Well, the answer is sometimes, right? Like if the string view lives long enough, it's fine. And if it doesn't live long enough, it's not fine, right? So this may or may not be safe. And Rust is not okay with that. So Rust is going to say, if you're going to do something like this, you need to make the demands that are necessary to prove that this is always safe. So what is this error? Says data flows from S into V. And it's what exactly that means is a little bit vague, I suppose, but we know what's happening here, right? We know that we're putting S in V and that's not okay here. Like S doesn't live long enough compared to V. So in order to make Rust okay with this helper function, which is basically, in order to make Rust realize that this line is the problem and not this line, right? We need to add annotations. So this next slide is about lifetime annotations in Rust. Now, to be clear, this is a little bit advanced. So this is here, you're peering into the future of Rust learning here. So, normally we wouldn't do lifetime annotations on the first day or anything like that. But this is sort of the nuts and bolts of what's happening. Rust has a view of the lifetime of every reference. And when you're doing interesting things across function boundaries, you need to tell Rust what you're doing. So here, the Rust code from the previous slides on the left, here only the first line has changed. Everything else is the same, but we've added this tick A. So on the left, we were saying vector of string views and a string view. Who knows where they came from? Who knows how long they live? Right? We weren't making any guarantees. And Rust didn't like that because this push requires certain guarantees, right? Now we're making those assertions. We're making those demands on the caller. So this tick A is what's called a lifetime annotation. And it's basically just kind of giving a name to the lifetime. So, these are angle brackets, right? This is also where you might put your type T, right? If you were generic over some type T would go in here, just like in C++. And lifetime annotations also go in here. They're sort of part of the type system. So what we're saying is, if the lifetime of the strings in this vector, if we call that A, then the lifetime of this string that you're giving me, that I'm going to put in the vector, well, that had better be A too. We're basically saying that these two things have to live for the same time. We're asserting that S lives long enough to be inside of V. Now, the technical nitty-gritty details of what's happening here are a little bit theoretical. The lifetime system is I think it's technically a constraint solving system. But the details don't really matter here because what we're doing in this case, it kind of makes intuitive sense where we're just saying that S needs to live just as long as all the other things in V live. We're giving them the same lifetime name. Interesting to note before we move on, there is a third lifetime here, which is unnamed. So this mutable reference to the vector, which is what allows us to mutate it, right? If we're going to call push, we need permission to mutate the vector. Our reference to the vector needs to be non-const, right? We're pushing into it. That has no lifetime requirement at all, right? We're not retaining that reference to the vector itself. We're not putting that in anything. We're just using it for the duration of this function and then relinquishing it. So no annotations are required at all. But this interesting move that we're putting, I shouldn't say move, this interesting maneuver that we're executing with push, that requires lifetime annotations here. So again, this is just planting the seed. You don't have to memorize this. We usually don't need to make these annotations, but when we do interesting things with pointers, often when we write, for example, iterators into a container, interesting things with giving out pointers into something else, in these cases, we sometimes need to reach for explicit lifetime annotations like this. This is what they look at. This is what they look like. So with that lifetime annotation added, now what has happened? Well, the error is where it belongs, right? Of course, this program was never valid. It was just as invalid as the C++ was. But now Rust can see that this helper function, my pushback, is fine. No problem there. It's making the demands of its caller that are needed to prove that the body is safe. And then now Rust can see that my pushback is doing something bad, right? So here it knows like, these two parameters, they have a lifetime constraint on them, right? This function is going to do something that requires this thing to live as long as this stuff. And it can see obviously that they don't. It can see that my string and my vector have very different lifetimes that are totally incompatible with the requirements of this function. It can see that. We get the expected error, right? Borrowed value does not live long enough. So we've sort of gone back. It's the same error as before we invented this little helper function. So that's what sometimes explicit lifetime annotations are required for. One of the first times I gave an early version of this talk, I got a really great question, which was, we're going to see a lot of other C++ types like shared putter, the kind of types that are modern C++ relies on to help manage the lifetimes of objects and avoid some of these pointer issues. Right? And the question was, would it be possible for C++ to add more features and more, smart pointer types and things like that? Would it be possible to expand C++ to accomplish similar things to what Rust is accomplishing? It's a really good question. And certainly, to some degree, yes. I mean, certainly there's a lot of room for new research and new tools for analyzing C++ code. But I think this example is a good way to see why you kind of need a new language to really solve this problem. So this concept of lifetime annotations, I mean, it's of course it's syntax, right? It's a special syntax. But the important thing is to realize that this is happening, this lifetime analysis is happening at every function boundary. With every data structure that holds a pointer, it's making some explicit, claims, assertions about how long those pointers live. So every time a reference crosses some sort of abstraction boundary, these requirements are communicated across that boundary. That pervades the entire language. And the entire Rust standard library, is built to accommodate this, right? Either, sometimes it doesn't require anything special, but especially for things like iterators, which are giving out pointers into other containers, they participate in this system, and everything participates in this system. So even though lifetime analysis is sort of function local, so each error is just based on what I can see in the context of this one function, because every function is doing it, you get these global guarantees. And that really does pervade the language. It's very difficult to add that on after the fact, I think. Because if you drop your lifetime metadata at any particular point, you sort of lose, well, I wouldn't say you lose everything, but you lose a lot. You really want to have this be a global system that everyone is participating in. And that's sort of my version of why I think, to accomplish the Rust project, what Rust is trying to do, it needed to be its own language. It would not be possible to just extend C++, for example, to try to get these kind of guarantees. You could catch some errors, but it would be very difficult to be this comprehensive. So That was lifetimes. Usually they are doing what we expect. They catch bugs that we know we shouldn't be writing, but sometimes they require explicit annotations. Not usually, not always, but sometimes. Big idea number 2, if you remember from that early slide, is mutable aliasing. So in the previous section, we were talking mostly about shared references, like const pointers. Now we're going to see a lot more mutable references. So let's jump right into the first example. So here we have an integer, and we're going to take 2 pointers to it. In this case, we'll use C++ references, but those are basically pointers, right? And we're just going to use those 2 pointers to increment the integer by int. And it's going to be 7, right? This is totally reasonable C++ code. Maybe a little weird. Obviously we don't usually need to create 2 pointers to the same thing, but you can. It's totally allowed in C++. And the big idea number 2 here that we're going to see in Rust is this is not allowed. And this will sometimes feel surprisingly restrictive. So this is a simple example of that. Like, what's wrong with this code? Well, Rust just doesn't like that reference 1 and reference 2 exist at the same time. It's not okay with that, right? First mutable borrow occurs here. Second mutable borrow occurs here. They overlap, right? We're using them at the same time. It's just not allowed in Rust. Mutable aliasing is not allowed. That is a very strong restriction. So, in the previous section, we were mostly looking at examples where the C++ equivalent would compile, but then do something crazy at runtime, right? When you violate lifetime rules in C++, yeah, that's a bug, right? We all know we're not supposed to do that. So the lifetime rules don't always feel too restrictive. They sometimes feel very helpful in Rust. But this second rule, the no mutable aliasing rule, this can feel pretty restrictive. You can look at this code and you can think like, man, why can't I write this code? Well, we're going to talk about why. But one more example of the same, and this is another example where, you'd think this code seems fine, right? So what's it doing in C++? We got 2 characters. I'm going to take a reference to the first one. We're going to take a const reference to the second one. And then we're just going to assign the second one to the first. So we want the end result, the array should be BB, right? And of course, we don't need to use references for this, but just for an example, right? We're using references here. Take a reference to the first, reference to the second, use them to do an assignment, right? And this is going to violate the aliasing rule, right? Because the first element here is a mutable reference. The second reference is going to conflict with it, even though the second one is not mutable. Mutable references must be totally unique. There can't be other mutable references or other shared references. So we'll see this is the error that Rust is going to give us. Same as in the previous slide, right? Here, maybe that's a little more surprising because, we know, for example, in this array, that the first character and the second character, they don't overlap, right? They are a reference to the first and a reference to the second. Those are disjoint things. They're not actually aliasing. Right? We know that in our heads. And Rust is basically telling us that it doesn't know that. You could sort of think of this as like Rust doesn't know that 0 doesn't equal 1. You could sort of see it that way. Another way to think of it is that, of course, array indexes can be variables, right? They can be any number, calculated at runtime. And of course, at runtime, with a non-const variable, Rust would not be able to prove that it doesn't equal the other index. And so the knowing that 0 is not equal to 1, that would be a special case of 2 const indexes, and Rust doesn't have that special case. So you could think of it that way, but it's kind of surprising that this code doesn't compile. And this is the sort of thing that new Rust users will run into, and this can feel pretty frustrating because to write code like this, if you decide that you want to take a reference to multiple references into the same array, you need to use some strategies in Rust. There are various ways to do this sort of thing, and they take some learning. So we'll look at some of them. The list on the left is sort of probably not comprehensive, but it's a list of a lot of options that you have for solving problems like this. In kind of in order from the ones that I like the most to the ones that I like the least. You know, I'd reach for the first one before I would reach for the second one, before I would reach for the third one, and so on. And we'll talk about a couple of them on the right, because I think they're interesting. So to do something like this in Rust, you know, you have to reach for one of these strategies. Obviously, just use indexes is a pretty simple strategy. If we weren't trying to keep references here, if we just did an assignment from, you know, char array 0 equals char array 1, that would work just fine. And many times when you have a reference issue like this, you know, the solution is to just take indexes into your vector or into your slice or into your array instead of using references. You know, often we can get away with that. Pattern matching is a little fancy. More recent versions of Rust allow you to structurally match on an array. I'm not going to show that, but that's an option you have here. That's a pretty good option. The first one I want to talk about is split at mute, which we see here in the top right. So the idea of split at mute is we call this method, we give it an index, and it's going to take the array or vector. It works on slices, which can represent a view into either an array or a vector. We won't talk much about slices, but they're very important in Rust. So it takes any view like that, and it splits it into two views, right? So you're going to have all the left side of the array and the right side of the array split at some index. Here, split at index 1. And it's just going to return that as two separate slices. So here we get this, it's returned as a tuple, and we destructure that tuple here. First slice and rest slice. So first slice is just going to be the view into this array that just includes the character A. And rest slice is going to be just the view that includes character B. And then here we can take a mutable reference into the first slice and a shared reference into the second slice. And Rust has no problem with this, right? Because Rust knows that once you've got these two slices that are actually both mutable slices, it knows they must not overlap. You know, it doesn't necessarily peer into the guts of split at mute, but it knows that split at mute must be abiding by the rules. So if it returned two mutable slices, well, great, those must not be overlapping. So if those aren't overlapping, then there's no problem taking these two references into them, and it works just fine. So this code compiles, gives you the result that you want. Here, before we leave this slide, I want to show a brief example of unsafe code. The skull and crossbones are there because we don't use unsafe code. Whenever we have a choice, you know, we would never actually use unsafe code for something like this. We would use any of the other strategies first. But I think it's very interesting to get just a little glimpse into how unsafe code works. So the idea here is we have these special pointer types. So these are not mutable references and shared references. Instead, what we do is we actually, in here, we implicitly cast it to a raw pointer, a mutable raw pointer to the char, a raw pointer to this char. And raw pointers are like references, but they don't participate in the lifetime system, right? So if you want to use them, if you want to dereference a raw pointer, you can only do it inside of an unsafe block. So what you're telling Rust is, hey, I know you can't prove that this is safe, but I know for certain that what my code is doing is sound. So I'm just going to do it. Close your eyes. Don't ask too many questions, right? That's unsafe. So this works. This compiles. This code is correct. Now, yeah, like I said, we would never ever do this in regular day-to-day, char string code. Wouldn't do that. You see unsafe code in the the guts of standard library data structures, things like that. The most common reason that we would write unsafe code in our own applications or our own libraries is most commonly would actually be to call C functions, right? To call into code that's written in C, maybe code in the C standard library, code in OpenSSL, something like that. We use those functions because C can do anything. Those functions are unsafe. That's the most common reason people end up reaching for unsafe. It also does show up in fundamental data structures. And I'm not going to show the implementation of split at mute, but I think it's a really interesting example to think about. So how does split at mute, which we just talked about, how does that work on the inside? How does it actually accomplish this? And the answer is that it does use unsafe code on the inside. So split at mute is a method in the standard library on any slice or array or vector. And it does use a little bit of unsafe code to construct these two slices that it knows are not aliasing. It checks the bounds. It'll panic if the bounds are bad, and it'll construct these two unaliasing slices for you using unsafe code, and then that gets returned to us, and then we can take advantage of the fact that Rust can now see that these are not aliasing, right? So the idea here is that unsafe code has been kind of encapsulated in a safe method that does all the right checks, solves the problem for us, and that's pretty much always the goal with unsafe code in Rust. Is sometimes we need to do things that the compiler can't understand, but when we've done that, we want to wrap it in a safe API so that safe code can take advantage of it, can use it and call into it without the possibility of breaking the rules, creating undefined behavior. So this is sort of just two cherry-picked examples of how you could solve this array, multiple references into an array problem. Again, I should emphasize, if these were both shared references into the array, we would have no problem, right? This only gets difficult because one of them is mutable, right? That's when that mutable aliasing rule comes into play here, and we have to reach for one of these strategies. We don't have time to talk about all the others. Cell and ref cell are very, very interesting. It's sort of, if you get a chance to learn more Rust and get comfortable with the standard library and all that, I think exploring how all of these work is a really interesting tour of all the fancy tricks that Rust's, object model and ownership lifetimes and borrowing, ideas can do. For now, we're just going to look at these two, and then we're going to move on. So anyway, this array stuff, these aliasing issues, this can feel very restrictive, right? Like, man, look at this. We have to jump through these hoops just to write into an array, like just to take references to a couple elements, to take mutable references to a couple of elements. Yeah, and this is a cost that Rust asks us to pay. And now we're going to see sort of what we get for our trouble. So like, why does Rust have this rule? And the answer is mostly going to be about safety. We'll look at ways that you can mutate a container to invalidate references. We'll look at multi-threading in just a moment. But 90% of the reason why we have to think about all this is safety. But before I get to that, I just want to touch on the 10% of this that is actually, it's not about safety. And I want to sort of show a quick example of how mutable aliasing can kind of have an effect all the way down the abstraction stack of the language. So this is a screenshot of an example in the Godbolt compiler explorer. If you have not used Godbolt, it is so cool. And actually, this image and all the other images in this talk, this is a clickable link. So if you get the slides, which I will totally link to with this video, you can click on this image and it'll open up this example and you can play with it. Godbolt is fabulous if you haven't used it to kind of inspect assembly output before. Give it a try. It's a great way to try to kind of see what the compiler is doing in languages like C and C++ and Rust. And so here, we'll start in the top left here. We have a very simple function. We can see it's written in Rust on the right and C++ on the left. So what is it doing? It's reading from source and it's writing that integer value to dest, right? We have a const pointer to source, const reference, non-const reference to dest, and we're storing source into dest. But I've included this silly extra line here just for funsies, right? We have this extra dest equals 42. And the question is, does that do anything, right? We're assigning to dest twice, right? In a row. Does this silly line here, which we would never really write ourselves, does it have any effect? Can the optimizer just remove it, right? So you can see that this is C++ compiled with O3, maximum optimization settings. Here I'm using Clang, and Rust this happens to be the low-level flag for the Rust C compiler. We normally use Cargo to compile Rust, but here in the compiler explorer, we used Rust C directly. And the interesting thing, we don't have to be able to read all this assembly. This is x86 assembly, and it can be very difficult to read, and I'm not very good at reading it either. But we can see in this example pretty clear that 42 is still there, So the C++ code is still doing this assignment. It's still writing 42 to dest. Whereas the Rust code over here, it's pretty clear that 42 is gone, right? These two moves here are the same as these two moves on the left, the second and third. So it's doing that, dest equals source, right? It has totally skipped dest equals 42. Why, right? So why is the Rust compiler able to optimize this out, but the C++ compiler not? And the answer is the C++ compiler is correct. It should not optimize this away because these references in C++ could be aliasing, right? So source and dest could point to the same integer in the caller. If I have int x, right, I could say store xx, right? And if I did that, what would happen, right? Well, this first line would say dest equals 42. So that would assign 42 to x, right? So then I would say dest equals source. Well, source is also x, so that would now be 42. So the final value of x in that case would be 42, actually. So deleting this line would be incorrect in the case where the caller gave us aliasing pointers, aliasing references, right? And that is allowed in C++. And that means that the compiler has to be defensive about this possibility. There are situations where it can prove to itself that two pointers do not alias, but in general, the compiler always has to assume that they could. It has to be defensive, and that's why the optimizer leaves in this assignment to 42, because it has to respect the code as you wrote it. If that has any observable effects, it has to generate code that does what you said to do. And the Rust compiler over here, it knows it can prove to itself that source and dest do not alias. It knows they cannot alias. They cannot point to the same integer. Why? Because dest is a mutable reference. Mutable references never alias, right? That's big idea number 2. If you try to call store xx, it would be store ampersand x, ampersand mute x. That will not compile in Rust, right? That's a mutable aliasing issue. We just saw that in the previous 2 slides. Rust won't compile that code. So the Rust compile, the optimizer inside of Rust C, LLVM optimizer actually, knows that store of 42 is a no op. We don't need it. It can never have any effect. It's gone. So this is just a brief glimpse into how mutable aliasing is not just about safety. We're about to talk about a bunch of examples that are just safety and how you can create use after free and all that with mutable aliasing. And that's 90% of the story. But that 10% is about how mutable aliasing actually has a big effect on what the code in the language means and what the compiler is able to assume, and it affects the assembly that the compiler can output. So it is actually, it has many effects. It's not just about safety. It's mostly about safety, though. So let's see some safety. So here, if anyone who's written code with a bunch of C++ vectors has probably run into this problem. You have to be very careful with methods like pushback because they mutate the vector, right? So what's happening here? We have a helper function push int twice, taking a reference to a vector of ints, and we're taking an integer to push twice, right? We've done something a little weird, right? Normally you would take this integer by value, and here we've taken it by const reference. We've taken a reference to the integer. It's a little odd. We've done that for the sake of an example, because what's going to happen, right? We create this vector. It's got 1, 0 in it. And then we take a reference to the first element of that vector, to the 0. We take a reference to that 0. And we call pushInt twice with the vector and a reference to its first element, right? So a lot of people who've written a fair amount of C++ have probably seen this a lot, right? So what's going to happen, this first call to pushback, it's going to dereference the n, right? It's going to get that value, get that 0. It's going to push it back into the vector. That's fine, but what does it do? It means that the vector is going to reallocate, it may reallocate its heap storage, right? The vector, in this case, is created with enough heap storage for exactly 1 integer, and so when we push back another integer, it reallocates, it needs more storage. That means its storage is now in a different place on the heap, and the original memory that it had for just that 0 is freed by pushback, which means that this reference into the original memory is now dangling. And so the second call tries to dereference and again, dereferences a dangling pointer, and who knows what happens, right? You can't do that, right? If you run your code under asan, it will tell you that this is a heap use after free. Don't do this. If you run your code under valgrind, it will tell you don't do this. If you run your code without either of those things, it'll do something. It might be a 0, it might not be. This is a classic dangling pointer issue, and what we see here is it's not a lifetime issue. It's not using scopes, right? It's not just that the vector has gone away. It's something more complicated. It's that pushback has changed the insides of the vector, right? It has invalidated any pointer, or what C++ would sometimes call iterator, into that vector. Those, you can't use those anymore. So when we look at this code all together, what we say is, this code to pushback means that this reference to my int reference is not valid anymore. So that's what we see. That's what happens. What happens in Rust? In Rust, this is a compiler error. Good, right? Like this would be a use after free, right? We're not supposed to be able to do that. What's interesting about this compiler error, remember the last time we made a helper function, what was it called? My pushback, right? The last time we made a helper function, Rust didn't like the helper function, right? Rust wanted us to put some lifetime annotations on it, because we were doing something fancy with the string view. Here, Rust has no problem with this helper function, right? No problem at all. Because what are we doing? We have a mutable reference to a vector, and we have a shared reference to an integer, and the mute reference. Remember the fundamental rule, big idea number 2, right? Mutable references never alias. So Rust is confident that, well, actually, it's like big idea number 1 and 2 come to work here. Mutable references never alias, and references are always valid, right? So I was given this ref I32. I am allowed to assume that that reference is valid for the duration of this function, right? Or if I do fancy lifetime annotations, maybe I can assume it's valid for longer than that. But here with no annotations, I can assume it's valid for the duration of this function. It's not going to randomly become invalid through some side effect. No, if I have a reference and my code compiles, then that reference is valid, right? So Rust sees this. It says you're dereferencing a valid reference twice. Sure, no problem, right? Rust sees no problem with this at all. Rust immediately sees that this line is the problem, right? What is this doing? Aliasing mutable references, right? It knows that my int reference, it's not a reference to the vector itself, but it's a reference to something in the vector, right? Vector is a library type. Rust doesn't really know what it's doing, but it knows that we borrowed it, right? It knows that my int reference is somehow borrowing my vector, and that's good enough. So I cannot create a mutable reference to my vector while my int reference is alive. That violates the aliasing rule. This code will not compile. So that's good. This is a very common mistake for beginner C++ coders, right? Like being able to invalidate a pointer by mutating the container that it points into is very easy to do without necessarily noticing that you've done it. This code, if we had an int reference that was to a separate variable, this code is totally fine, right? It only became a problem when we happened to have aliasing references. Now, this is a simple example, right? I mean, a lot of people who've been writing C++ for a while can spot things like this. They know they have to be careful with things like this. They might not write this code. But I want to link to a great YouTube talk. So Herb Sutter is a famous C++ guru, right? Author of a lot of books and gives a lot of talks. And this is one of his talks. I think it was from 2014. Talking about modern C++ style, smart pointers, shared putter, right? The right pointer types to use in various situations. And in this talk, he goes into a common bug that happens with shared putter. So larger code bases that use shared putter can basically commit exactly the same mistake we just saw with vector, right? You can somehow dereference the shared putter, get a pointer to the thing inside of it, through some sort of aliasing, mutate the original shared putter, maybe drop the reference count associated with your pointer to 0. Maybe now that's a use after free. This is a 5-minute section of a big talk that Herb Sutter gave to, CPPCon attendees, right? Professional C++ developers about this is on his slide of crucial rules about pointer types, right? You need to be careful with shared putter in C++. So even if we sometimes think, oh, we wouldn't make that mistake with vector, there are a lot of versions of this mistake, and some of them show up in talks aimed at C++ professionals. It does happen all the time. This image is also a link. This links to the relevant section of the talk. It's a great talk. I mean, all of Herbstadter's talks are amazing. This links to the section that talks about shared putter. If you have time, if you're clicking through these slides, watch that section of the talk. It's about 5 minutes. So that was an example of how mutable aliasing combined with references into containers, right, can cause use after free, right? Can invalidate references, and that's a single-threaded safety issue, right? But we also often, run into aliasing issues with multi-threading, right? So another way to commit undefined behavior in C and C++ is to have two threads that are at least one of which is mutating a value while other threads are reading or mutating that value. That's a data race, right? That's another reason why we rely on the big idea number 2, right? The mutable aliasing rule for safety. So here is this is almost an intro, but we'll use the structure of this slide on the next slide as well, and into modern C++ multi-threading. So, spawning our own threads is the old-fashioned way, right? When we do multi-threading today, we like to use these fancy sort of iterator-based, tools that automatically parallelize everything for us. So this is an example of multi-threading code that's all good. So the code on this slide is perfectly correct. So here we start with just a simple regular for loop just to get the behavior clear. So we have a vector of ints. We're going to loop over it. We're going to increment each integer, right? That's what each of these examples is doing. In the second example here on the left, we translate that serial for loop into the standard for each algorithm, which is going to do exactly the same thing, right? It's going to go over the vector from beginning to end. We use a lambda here. So the body of the for loop becomes a lambda. Here its capture clause is empty. It's not capturing any variables outside of itself. And this argument, this reference to the integer, this lambda is going to be called for each element. So this loop is going to do exactly the same thing. This is exactly the same loop. But the neat thing about for each, as of C++ 17, is it supports this magical parallel mode, right? So you can say, hey, C++, run this in parallel, right? And of course, the for loop, the original for loop, that's serial code, right? C++ is not within its rights to magically parallelize that. But if you use for each and you tell it to, it will magically parallelize this. So your code needs to link against libtbb or something like that, which will create some sort of global thread pool, and it will use fancy work stealing techniques to figure out how many threads to bring to bear on this problem. And of course, this is a silly example. You're adding one to each element. That's kind of silly. But if we were doing a bit more work for each element, this could be a huge speed up, right? Like we rely on multi-threading to get high performance, application code on modern multi-core processors, right? This is a big part of modern programming. And these fancy modern parallel for each loops make it a lot easier than it used to be. These are very, very cool. So sometimes we can just add, 10 or 11 characters to our program and just magically it's 8 times faster, right? It's truly amazing. This stuff is great. On the right, Rust is doing exactly the same thing. So we can mostly glide over it, right? A regular for loop, iterating over a vector the regular way. In this case, it's going to get an iterator to mutable references to each element. Here, using the for each method on iterators, right? Just like the for each algorithm, we now have, Rust calls this a closure. It's like a lambda. The type of the X variable is inferred, but it's doing exactly the same thing. Rust doesn't have the plus operator, so we use plus equals instead. It's doing exactly the same thing. Here we can see that the dereference of that pointer that it's getting is explicit. Excuse me. And very similar, right? We can just change a few characters, right? And our itermute becomes par itermute, and we can do the same thing magically in parallel with thread pools and work stealing and all that fun stuff. In this case, this is not standard library Rust. So to be clear, this is a third-party crate. It's a library that you can use. It's called Rayon. It's very commonly used. It's almost a de facto standard. It's not technically in the standard library, but close enough. And par or mute, right? It's sort of the same idea. You sort of added a few characters that say go to town, right? Magical multi-threading. This stuff is great. But the perils of multi-threading, right? It can be easy to shoot yourself in the foot. So here, each of these loops is doing exactly the same thing as before, but I've added, what have I done? I've added a local variable sum. So in addition to incrementing each element, we want to accumulate the values of all the elements in sum, right? Which for a for loop, for a serial for loop, is a perfectly reasonable thing to do, right? This is normal code, right? We do this all the time. Here with the for each lambda approach, again, totally reasonable code. We do this all the time. The capture clause of the lambda, I've added this ref little sigil here. So sum will be implicitly captured by reference. But this code does exactly what it looks like, compiles to exactly the same code as the first one. This code is totally legal. And only when we get to the parallel version do we run into problems. So I've included all 6 samples on this slide also, because I want to highlight that it's only when we parallelize this code that this data race against the shared sum variable becomes a problem. Because what is this code doing, right? So many threads, who knows how many threads, will be executing this line at the same time. It's the classic ATM problem, right? You read your balance, you increment the number, you write the new balance, but 2 ATMs are doing it at the same time. They stomp on each other's work, right? You get the wrong answer. And that's true here. You're going to get the wrong answer, right? Some of your increments will be lost when you run this code. You'll see that sum does not come out to be the actual sum. And if you run this against thread sanitizer, it's going to be mad at you, right? This is a data race. It's not just the wrong answer, right? Data races are worse than that, right? They're real undefined behavior. The compiler is allowed to miscompile your program in surprising ways, right? If you write code like this. So these, I include all this code on the slide to highlight that it can be very subtle. This transition to multi-threaded code means that something that used to be fine is not fine anymore. And so this is a common foot gun with multi-threading. You have to be very, very careful not to mutate shared state without synchronization, right? This Rust code, again, doing the same thing, right? We've added the sum variable to each example. And in this case, the bottom right here doesn't compile, right? Thank God. Rust knows that we've made a mistake here. What does it say? Captured variable in a fun closure. It can be a little bit confusing what that means. It turns out that fun is a trait, which is sort of like a C++ concept. And we're not going to get into exactly what that means, but we know what the problem is, right? Like this closure here, this lambda is not supposed to be mutating shared variables because it runs on multiple threads. We know that sort of conceptually. And this is how Rust catches it. And I think it's very interesting to highlight, another reason to include all these examples on this page. It's very interesting to highlight that this example, of course, we said the serial for each loop, just like the regular for loop, this code is totally fine. Rust compiles this code without complaining at all. There's nothing wrong with this code, even though it's also capturing sum in a closure. It's also calling that closure in a loop. Rust only complains for this code, which is good, right? It complains for the code that's wrong and not for the code that's right. But the interesting question here is, how does Rust know? Like, how does Rust know that this code is illegal, but this code is legal, right? And the answer, like we said before, this analysis is done. Each function guarantees in its signature. It makes the demands of its caller that it needs. So Rust will figure this out purely based on the signatures of these different for each methods. And I'll include these here. This is code that has been copied straight out of the standard library on the left. You don't need to read, you can ignore the body. In fact, I'll just sort of darken it. The important thing here is that this code is making a trait bound. This is saying that the F closure type must satisfy this trait. Again, it doesn't matter exactly what funmut means, but you know, intuitively, it's allowed to have mutable references to things, right? Funmut. Whereas fun doesn't have the mute. It's not allowed to have mutable references to things on the outside. It's not allowed to capture mutable references, right? So these, again, this syntax is not super important right now, but the important thing to realize is these functions distinguish in their signatures what types of closures they're allowed to take. And that's how Rust does things, right? Each function has to say what its requirements are, and then its callers only need to know about those requirements from its signature, and everything will work. You can see that, of course, there are some other things going on here. Send and sync are other traits that involve other threading issues. And we don't have time to go into all of them, but there's quite a lot of sort of richness in Rust's type system about what the threading properties of any given object are. And so you can make very subtle, distinctions between what each function is allowed to take and what it's not. The details don't super duper matter, but the important thing is for each has declared that it is happy to accept a lambda, a closure that has mutable references, and rayon for each, the parallel one, which is I've copied from the rayon crate here, has declared that it's not happy to have those. That's how Rust knows. So if you do want to write, code that mutates shared state, right? What do we have to do? We have to synchronize it, right? And this is an example of some, somewhat complicated concepts. Obviously, not everyone has seen atomics in C++ before. But I just want to go over these examples a little bit briefly, just to demonstrate that the same way you're supposed to solve this problem in C++, that also works in Rust, right? When we do the right thing, the compiler will actually compile our code, which is nice. Here we're using an atomic add to increment sum, and you can see that Rust is doing basically exactly the same thing, just very slightly different naming of the parameters. It's exactly the same thing, and maybe surprisingly, Rust will compile this code. This code is correct in C++. It does get the right answer. Gets the right answer in Rust too. Rust will compile this. We'll run it. Works fine. Should we be using memory order relax? Well, maybe that's juggling chainsaws, as Herb Sutter likes to say. But if it's there, if you want to use relax atomics and you feel confident that you understand what they do, they are available to you. They are safe. How does this work? Rust knows that the fetch add function does not require a mutable reference, does not require a unique reference to the atomic. It actually works through a shared reference. It's sort of an interesting escape hatch in the rules about shared versus mutable references and mutability. So this code works just fine. More generally, obviously atomics are mostly just about ints. More generally, if we want to synchronize any type, we would use a mutex, and that works in C++ and Rust. I want to touch on this briefly here, and it will come up again later when we sort of reach our final section. In C++, we can create a mutex here, and then I use a lock guard to lock that mutex. So this type will, in its constructor on this line, locks the mutex, and in its destructor at end of scope, when the lock guard is destroyed, it unlocks the mutex. So it guarantees that we don't forget to unlock, and it also guarantees that this code is exception safe. If sum plus equals x obviously is not going to throw, but if something in here threw an exception, the lock guard would still be destructed properly at the right time on the way out, and the lock would still be unlocked. So that's very good. Lock guards are great, right? We should be using lock guards when we use locks in modern code. Rust is the same. There is one substantial difference, which you might notice immediately, and that's that the mutex type in Rust is actually a container. So it's a mutex of i32, and we pass in the initial value 0 in the creation of the mutex. So then we create the lock guard basically the same way. There's a lock method that's giving us that guard. It's doing the same thing. Its construction is locking the mutex. Its destruction at end of scope will unlock the mutex. But the other big difference we notice is that we actually dereference the guard to get at the sum variable on the inside and add x to it. So this, what we were doing over here is sum plus equals x with a separate variable, is happening here. Star guard is a smart pointer, right? It's giving us access to the integer that's contained inside. And of course, this is a mutex, so this integer could be any type. could be another vector, it could be a string, it could be anything. And the guard, we're sort of syntactically required to lock it, because we have to use the guard to actually get at the value on the inside. So that's a big part of the safety story here. Rust won't let us just assume that a mutex synchronizes some value. The mutex must contain that value. But this code works just like the C++ code works. So keep mutex in the back of your head. We'll see a little bit more about mutex in a bit. But for now, I want to talk about big idea number 3, which is move semantics. So here's another slide with a lot of words on it. Big ideas 1 and 2 were about references, right? Big idea number 1 was references are always valid. You know, if for their lifetime, if you have a reference, it must be valid. Big idea number 2, no mutable aliasing, right? Big idea number 3 is about how move semantics works. So this is the last big idea I want to really hit on before we get to our final section where we kind of tie it all together. So like the other wordy slide, right? Familiar ideas on top, new ideas on the bottom. So plain old data types, you know, what we think of in C++, and I think C++ refers to them as trivially copyable. I could be wrong about that, but you know, it's an int. A structure of ints might also be a plain old data type in C++. A standard array of ints would be a plain old data type. Things that you can just bitwise copy from one place to another, right? Often they don't hold pointers, but they might. So in Rust, these sorts of simple copyable types they're called copy, and copy is a trait. And again, we're not talking about the trait system and generics and all that stuff, but we'll use the word. So we'll say these types are copy. And what that means is that when you do a by value operation on them, you copy them. So what, a by value operation, typically when you name a variable, you're using it by value. So if you say x equals y, you're taking the value of y and assigning it to x. If you say foo of y, the foo function, you're passing y by value into foo, And with copy types, as in C, it's when you by value operations, using a value, passing it to a function, returning it, they just make a copy. This is a bitwise copy. The bits of the type are copied to a new place, right? Same is true in Rust. And trivially copyable types in C++, I believe, are the same. This is one of the places where I'm not totally clear on all of the ways that C++ can categorize types, but I know it's close to that. We can think of it in terms of C, right? So you move around in I32, just like in C, it's copied, right? And interestingly, before we move on, ref T, right, the shared reference to T, that's a copy type. Now, the shared reference has a limited lifetime, right? We can't keep a shared reference outside of the scope where it's valid. But within that scope, we can copy it as much as we want. We can make 3 shared references to the same value. That's totally fine. Shared reference is copy, right? And then other types that do, richer, more interesting things are not copy, right? So a vector of ints, a vector of I32, it owns a heap allocation, right? The vector is, in Rust, it's a pointer capacity length. In C++, I think it's pointer, like begin, end, and capacity end. Same idea, right? So it's referring to an area of heap storage that it has allocated, that it owns, right? And so, of course, we can't copy a vector bit for bit to another vector, because then they would both be holding a pointer to the same heap storage. So that would be, among other things, it would be a double free, right, when they're destroyed. And we obviously can't double free heap storage. It would also violate the aliasing rule in Rust, right, if we could do that. So types like vector that own heap memory are usually not copy. They can't be, because they have to uniquely own that memory. Something like a file object that owns a resource, like a file descriptor, right, would also not be copied, because you need to make sure you uniquely own that file descriptor so that you don't close other people's descriptors, right? So that's familiar from C++, right? So like non-trivial types, like not plain old data, not pod, not trivially copyable, that you don't just make bitwise copies of them when you pass them around, right? Something more interesting happens. And we can note that a mutable reference in Rust is also not copy, right? Mutable references cannot be aliased. And that means that if you want to take your mutable reference and assign it to a different variable, well, It's not, you can't just copy it. So here's big idea number 3. So what happens when we do by value operations on non-copy types in Rust, right? What happens when you pass a vector by value to a function, right? So those are moves, right? So whenever you use a non-copy type by value, you move it. And what move means is destructive bitwise copy, which is maybe surprising, right? So like a move is also a bitwise copy, right? We just said that when you use a copy type like int, you pass into a function, its bits are copied into the function stack or something like that. That's also true of moves. So moves in Rust just copy the bits from the moved from object into the moved to object, right? So this is unlike C++. In C++, you have a move constructor, which is code that it might be defaulted by the compiler, but you might also write that code. It's arbitrary code associated with your type. In Rust, moves are bitwise copies, always, just like for int, right? The difference is they're destructive. So what we mean is that the moved from object, the source, is like gone. It's like, I like to call it evaporated, right? It disappeared into thin air, right? And in particular, it's destructor. Actually, the word destructive is a little tricky because it's the destructor of the moved from object in Rust is never called. And that's important because if we just said that moving a vec is going to make a bitwise copy of it. If its destructor was called, they'd be pointing to the same thing. So the destructor of the moved from object is never called. That's what destructive means here. And so if you ever try to access that value again, Rust is not going to compile your code. When you've moved from a value, that value has evaporated into thin air. And while we're at it, everything is movable. Right, so in C++, not everything is movable, right? A type might or might not have a move constructor. In Rust, everything is movable. Moves are always bitwise. And if your type is non-copy, that move is destructive, right? So it's almost a bit inverted. You could kind of say that a copy is a type of move in Rust. Like a copy is a move that doesn't evaporate its source. So you could think of it that way if you want to. But everything is bitwise. That's part of the key idea. And for that reason, we have to make sure that no one ever touches a moved from object. So that's a big difference from C++. So we're going to see some examples of that. So here we're moving a string, right? And not everybody watching has probably carefully learned move semantics in C++. So I'll use this as an opportunity to talk about what the C++ code means for folks who maybe are more familiar with C or haven't brushed up on like standard move in C++ since C++ 11, I believe. So here, S1, string S1, right? So this is a heap allocated string, right? So it's going to be pointing onto the heap. It's going to write these characters there. And we say S2 equals move S1. So what that means is S2 is going to just steal the heap pointer from S1, right? So this does not make, this line does not make an allocation, right? This line right here does not allocate. S2 just steals the heap pointer from S1. And in this case, it's gonna null out that source pointer. So it's gonna leave S1 in basically an empty state. And then similar idea, we can push S2 into a vector. Here we say pushback of move S2. And what's going to happen is that the new element in this vector, that's going to be a vector of one string, right, will have stolen the heap pointer from S2, right? That's what this code means. So here, because we allocate this, so we've basically made one string allocation, but then each of these moves has kind of stolen that allocation. So in total, we only make one string allocation in this code. But one thing I want to highlight is that these S1 and S2 variables, they still exist. So the destructors of these guys will still run at the end of scope. It's just that because they have a null pointer or they're empty or whatever internal state. They've been emptied. So their destructor will do nothing. But the destructors still run. And I want to highlight that because that's the key difference in what the equivalent Rust code will do. So in this Rust code, creating a string, just like in C++, this string is going to wind up on the heap. Here, S2 equals S1, this is a move. So in C++, when we want to move things, we use the standard move function. In Rust, this by value usage of S1, this by value assignment into S2, is a move. That's what assignment means. And S1 is a string, not a copy type. So this is a destructive bitwise move of S1. And the same thing is going to happen here when we pass S2 to the vector. That is a destructive bitwise move of S2. So this is just, this is a method. This is parameter passing. This is parameter passing by value. That's a move. Remember, by value operations, assignment, parameter passing, returning, right? If we do those things by value, those are moves. This moves S2. And the crucial difference is, at the end of this Rust code, S1 and S2 have totally evaporated. They're gone. It's like they never existed, sort of. So their destructors will not run. They're not left in the empty state, per se. In fact, if you look at the debugger and inspect the bits of S1, they won't be mutated at all by this move operation. It's just that the compiler knows that S1 has disappeared into thin air and won't talk about it ever again. All right, so that's the key difference between these two pieces of code. One thing to highlight before we move on to talk about move semantics more is, in C++, if we don't say standard move, like this S2 equals S1 line. So here, remember, let me flash back and forward. So previously, S2 equals move S1. Now, S2 equals S1, right? The default behavior of assignment in C++ here is copying. And copying is not bitwise, right? It runs the copy constructor, right? It's code. And in this case, it will make another heap allocation. So S2 will be a separate heap allocation that has the same characters as S1 in this case. Same thing here, parameter passing by default. This is a copy. That's a third allocation. So this code allocates 3 strings on the heap, right? And if that's sort of the default when you use things by value in C++, without taking any extra steps, without calling standard move on that usage to make it an R value reference. That's the magic term, right? When you do things by default, they're copies. And to get the same behavior in Rust, it's not the default is move, right? So in Rust, we use the clone function. So a clone is like, it's a deep copy, essentially. It's similar to the copy constructor in C++. It will make a new heap allocation, right? The clone of a vector would make a new heap allocation, right? It's like a C++ copy. It creates a totally new object. And so this code is doing the same thing in Rust as this code in C++. And again, let me flash backwards and forward. So moving in Rust is the default. Copying, deep copying in Rust requires the clone method. Moving in C++ requires the move function, standard move. Copying in C++ is the default. So that's a syntactic difference. So we don't have to spend too much time thinking about it. But when you're reasoning about what code does, it's a pretty important syntactic difference. Rust, by default, likes to move things. Now, we can mostly forget about that and talk about how the moves are different between the two languages. So, like we said, moving in Rust is destructive, which means that if you try to use the moved from object, you can't. So we'll see that. So in C++, that's not the case. So here, I create S1. That's allocated on the heap. And then I move it into S2, just like the previous example. And then I print S1. Right? So my question is, what happens if I print S1 after moving from it? Right? And the answer is, in some ways, the answers don't do that, right? Like the standard doesn't say what state S1 should be left in. The standard says it should be left in some valid state. Now, I think in practice, what you're going to find is that any C++ implementation in the real world is going to leave S1 in the empty state. So when I print S1, what I see is that it prints nothing. It prints no characters. It contains nothing. And you'll probably see that consistently. But it's important to emphasize that is not guaranteed. That's not guaranteed. The standard doesn't necessarily force string to behave that way. And in general, people say, don't do this. Like, don't use moved from values, right? We're really not supposed to assume anything about them. The only thing we should be assuming about a moved from value is that when its destructor is called, that's going to be okay. That's going to do something reasonable, which is typically nothing. Not always, but it's safe to be destroyed. It will be destroyed automatically when it goes out of scope. Other than that, we generally try to avoid using moved from objects in C++ because we have very few guarantees about them. For certain standard types like vector, we might have a few more guarantees, but typically we don't want to make any assumptions. In Rust, this code will not compile. So here, right, use of moved value, right? So this is, we know that under the covers, S2 is a bitwise copy of S1, that we know that. And so we know, for example, that if we could use S1, it would be kind of an aliasing pointer to the same heap storage, which would obviously be bad, right? We could use that to break all sorts of rules. And of course, what Rust is going to say is you just can't use it. It's been moved from, it's gone. It has evaporated into thin air. If you try to touch it, like printing it here, the debug print macro, I'm just not going to compile that code for you, right? That's the situation in Rust. So in C++, we probably should not use moved from values. It's best to avoid that. In Rust, you cannot. That's a pretty big difference. Here's another example, and this one's a little more concerning. So this is the question of what happens if we try to move from a value while there are outstanding references to that value. So let's look at what happens in a C++ example. So here I have a string. It's shorter, and there's a reason for that. And what I'm going to do, remember string view from the first section. I'm going to create a string view from that string. So my view is basically pointing into the S1 string. And then I'm going to move S1 into S2. And my question is what happens if I print my view? And we really should not do this. We really should not do this. But C++ will compile this code, and actually asan, ubsan, and valgrind, they don't complain here. I don't think this code is technically undefined behavior. I think this code is implementation dependent behavior. And I believe if the implementation chose to do something horrible like segfault, the standard says that the implementation might choose that. Here, my implementation did not choose to segfault or anything like that. But it still chose to do something pretty weird. So what I see on my computer is that what was originally ABCDE is now null character BCDE. So my backslash null is like the C style escape, right? So that represents the null character here, and that's kind of weird, right? So moving from S1 has it has mutated what my view is pointing to somehow, right? So what has happened, right? What has happened is ABCDE, that's a pretty short string, right? So S1 is going to use the small string optimization. So this ABCDE is actually stored on my stack, right? Sort of locally in the struct, in the space of the string structure. And then when we move from it, so there is no heap pointer because the small string optimization is in effect. And so S2 is just going to copy the strings into its own small string optimization. It's going to copy the characters. And it does, for consistency, it wants to leave S1 in an empty state. So it ends up setting its length to 0 and writing a null character into the small string optimized storage, which mutates our view, which is this really weird outcome. And I assume that someone who knows more about C++ strings than I do can come up with something even weirder. This is a really good example of why you just really should not rely on what happens to moved from objects. In general, any reference into them could be invalidated. Sort of who knows what could happen. Now, if S1 was heap allocated, we would probably find that my view still looked the same as it did before. Probably in that case, the pointer would just be stolen. but we really should not be relying on these things, right? Moving from a value in C++ we should assume that it invalidates all the references into that thing. In Rust, it's going to be a compiler error. So it's sort of like we can't access the move from object directly. We also can't use references to it. Or another way to think about it is we can't move from an object if we have references to it. It's sort of like those things conflict with each other and it just won't compile. So we can see that here. So here, right, we've borrowed S1 as my view. We've moved S1 into S2, or we've tried to, but Rust can see that this my view borrow is still alive. It's still going to be used after this point. It's not a dead borrow. And so it's just, this is incompatible. Right? You just can't do this. You can't do this at all. The question of whether, string uses the small string optimization or not doesn't really matter. In the case of Rust, it so happens that it does not use the small string optimization. But even whether it does or not, you're not allowed to use this. It could have. Rust strings could have used the small string optimization. They don't. And either way, this rule doesn't care about any of that. The Rust says you can't move any value while that value is borrowed. So here's another example. And this one might be a little bit more surprising because here in C++, this works mostly. This is mostly reasonable. Whereas in Rust, again, we're not going to be able to do this. So I've gone back to the first example. I move S1 into S2. We move S2 into the vector. And then I've added another move, right? So we're going to move back out of the vector into S3. And in C++, this kind of does what you expect. This does work. It compiles and it works. In Rust, we cannot do this. This is not allowed. So let's see that compiler error. So what it's going to say is cannot move out of index of vec, basically. And this is so first I want to think about why should we expect this to be an error? And then we'll talk about how Rust kind of sees that error. But let's talk about our expectations first. So my question is, what should this code do? So in C++, we've moved out of v0. So the string S1 and S2 and also the string v0 have been left in some state, which is probably empty. And S3 contains the string and it contains the one heap allocation that was made. And that, that kind of makes sense, right? So these strings have been left in some state and the string in the vector has been left in some state, and we probably shouldn't use the vector again. It contains a string in some state that we don't want to think about. But that could make sense. Now, this would be a little weirder if V contained more elements. So say V had a few strings in it and we moved out the first one. So now V would contain one string that was in some state that we don't want to think about and a bunch of other strings that were still valid. That might be a little odd, but it's doable. You could do that. You should just try not to use v0 after that point. In Rust, remember the rules about how move works are a little bit stricter, a little bit more extreme, right? The original value is supposed to disappear forever, never to be heard from again, never to be referenced again, right? So S1 and S2 have evaporated. And then on this last line, what Rust would kind of want to do here, if Rust was going to compile this code, what it would want to do is evaporate v0, right? It would want to leave the first element of the vector, in this case, the only element of the vector, in some state that can never be touched again. But how would that work exactly? So with S1 and S2 here, I mean, these are local variables. So Rust, what does it mean to evaporate a local variable? Well, Rust just won't compile your code if you name that variable again, right? You just simply can't use it. But to evaporate an element from a vector, that's kind of odd. Does it evaporate the entire vector? Like, if not, how does the vector record which elements have been evaporated and which not? It doesn't really have a mechanism for doing that. The only reasonable thing that we could really do here and still satisfy all of Rust's rules is like move out of the first element and then like shift any other elements down. If there were other elements, we could imagine shifting them down, and that would leave the vector in a valid state with no disappeared elements. But it would be very, very weird if this assignment line here like popped the vector. We'll talk a little bit more about the removal operation in a couple slides, but like, so the summary I want to leave this slide with is, it's not clear what this line should do in Rust. Like, there aren't a lot of great options for what this could mean in Rust. So, in short, it just won't compile, which is probably for the best. So the next slide is sort of about the same problem, but in a more general sense. So how does Rust kind of view this problem? So the previous slide was a special case of this broader limitation. So here, what are we doing? We have a function f that takes a string by reference and then moves from it into a local variable. It prints that variable and then allows it to be destroyed. Now, notably, the string reference s1, the argument to f, it's not a ref, right? It's not an R value reference. It's a regular reference. Nonetheless, it is legal to write this in C++. It might be confusing. Maybe you shouldn't, but you are allowed to move from things that are passed as regular references if you choose to. So it basically moves from the string. That's what f does. So what does G do? It creates a string. It calls f with it, and we know that f is going to move from it. And then it prints that string. So this is kind of similar to some of the examples we saw before, right? What happens when we print a string that we've moved from? Well, on my box, it's empty. It probably in all actual implementations, it's empty, but technically we're not supposed to assume that. Now, of course, S2 must have the value that was moved into it. So we certainly are allowed to assume that S2 equals foo. This is guaranteed. That is what moving means. We have the value in the new location. So S2 equals foo. That's reliable. That's expected. S1 is empty string. Well, that probably happens most of the time. In Rust, we can't do this. This code doesn't compile. So what's it trying to do, right? So we have S1, and we're going to call f. Here I've used a mutable reference, which just is sort of, it's the equivalent. It's the closest thing here. And if this was going to work, if f was going to work, then this line, print S1, debug S1, this should be illegal, right? If f was going to succeed in moving out of S1, then we really should not be allowed to print it, right? S1 should be disappeared in that case. But so if this was going to work, then G should not compile in Rust. But it's actually f that's not going to compile. So what Rust is going to say is, hey, this let S2 equals deref S1, like moving out of this reference, like you're not allowed to do that. Like what Rust is actually going to say is this move is not valid. You cannot just take a reference to someone else's string, even a mutable reference, and like rip that string out and like evaporate the source. You can't do that because we don't necessarily know anything about where that string lives, right? Maybe it's someone's local variable, right? From the perspective of f, right? Where does S1 come from? Could be anything, right? It could be someone's local variable. It could be an element of a vector. It could be a member of some struct somewhere, right? It could be anywhere. And so if we're just expecting that we can rip it out of that place and somehow hope that the caller knows never to use it again, how could we do that, right? Like, would we set some flag? Do we want to mutate the vector? Like, what does that even mean? And the answer is, don't have to worry about what it means because we're not allowed to do this, right? We're simply not allowed to move from behind a reference directly. So the next slide will be about some exceptions, but this is just not allowed, right? So when G calls f with a mutable reference to S1, G is allowed to assume that once f returns, S1 still exists, right? The mutable reference is a type of borrow, and G is not giving up all rights to ever talk about S1 again. It's a temporary borrow, and that means that f is not allowed to just rip S1 out of existence. This code doesn't compile. And so it turns out that that's really what, I'm going to go back, that's really what Rust was complaining about with the vector also. So, how does indexing work? I mean, in C++ and in Rust, the vector has some indexing operation that returns a reference. What it actually does is it returns a reference to the element at that index. And so the indexing syntax might dereference that reference depending on what you do. But really what indexing is returning a reference to the thing. And so it turns out that the vector limitation is just a special case of this rule, which is you cannot move through a reference. And this is here, this is the more general error, cannot move out of S1, which is behind a mutable reference. We can't do that. We can't rip other people's objects out of existence and expect them to know that we've done that, right? That's not allowed. It works in C++, may not be advisable, but you can. In Rust, you can't do it. Now, there are ways to do it. So the simplest way is F may not rip S1 out of existence, but it may replace S1 with a different string. So here we see this is a standard library function. It's totally safe. Swap. So here I've created a local string. It happens to be empty. And I've swapped it with the caller's string. So this is totally legal. And what's going to happen is when we return to G, we still have a valid string S1. It has a different value now. It now is an empty string. But that's fine. You know, we're still allowed to print it. Its destructor will still do something reasonable. So swapping is allowed in general. So as long as you can replace the object that you disappeared, then you haven't created any problems. That's fine. It's also possible to use more interesting types to do more interesting things. So here I create an option string. It turns out that option is actually an enum in Rust. It's like a tagged union data-bearing enum type, and enums are a real big topic. And if we were really spending a week learning how to write Rust, that enums would be a big chapter. We don't have a lot of time to talk about it here, but functionally, option in Rust it is an enum, and it works like optional does in C++, the modern optional type. So it's a value that might or might not be present. Right? So here we have an option string, and what F is able to do here is it calls the take method, which will move out the value that the option contained. And in order to leave the option in some valid state, it will replace it with the I'm not holding anything value of option, which is in Rust is called none. So when we actually debug print S1 here, it'll say it contains none. It does not contain a string. So here we've used the option type to sort of enable a one-way swap, right? We've swapped in nothing, but nothing is a valid instance of the option type, right? And then finally, we talked about popping out of a vector, and of course, vector does, it does have a remove method, the same way C++ vector has an erase method, which we'll actually talk about more in just a second. So of course, if I have a mutable reference to the vector, then yes, then I can totally call the remove method. And this will do the thing that we kind of touched on before. So what's it going to do? It's going to remove the foo string. That's going to be moved out. That's the return value here. That's going to wind up in S2. So we'll end up printing, foo there. And then because it's a vector, right, we've removed the first element. So it will shift down the other two elements. It will update its length. It's not 3 anymore. It's 2 now. And so when we debug print the entire vector, it's going to print the 2 remaining elements, right? So if we know that things are in a vector and we want to use vector-specific methods, then we can do these shifting, popping operations. That's totally a thing we can do. It's just that indexing will not implicitly do this. That's sort of the limitation. So if we want to move through references, there are ways to do it. There are several ways to do it. Swapping is the most general of them. But we cannot just rip a value out of time and space through a reference. That would leave the caller in an unacceptable state. That is to say that whoever owns the thing the reference is pointing to would be left in some awful state, presumably crash or something. So that's not allowed. But these things, they leave the source of the reference in some reasonable state. These all work. So this has been a lot of examples of how move semantics in Rust works. This is because everything in Rust is movable. We actually have. There's a convenience function. Sometimes we want to move things nowhere, right? We want to evaporate them because we're done with them. So this is a convenience function in Rust that we have called drop, which doesn't really have an equivalent in C++. in the standard library that I'm aware of. But here in C++, we're creating a file object just for this example. And if we wanted to close the file object, there's a method for that. It turns out in Rust, the way you close file objects is just by dropping them, by just having their destructor run. And Rust is quite flexible with this. If you want to drop an object immediately, instead of waiting for it to go out of scope on its own, you just call the drop function. So any value that would be legal for you to move, like a local variable, that is any value that you have ownership of, you can drop with the drop function. So you'll see this come up in Rust, and we'll see it in a few slides down the road. One very interesting fact about the Rust standard library, which is half the reason I even have this slide. The other half is that we're going to use the drop function. But the most interesting fact about the drop function is it's actually the empty function. So you might expect that the drop function, which like evaporates a variable and causes its destructor to immediately run, you might expect that that has to be some sort of special compiler magic. It turns out no, because that's what moving means in Rust. Like if you call a function with an argument that you pass in by value, that value has been moved away. The function will drop it when it's done. And so the empty function is drop. So here it takes a generic type, so you can drop any type. But this is just what the empty function does, and for convenience, the Rust standard library defines an empty function called drop. So when we want to drop a file, we call the empty function on it by value. It's moved into that function, immediately destructed at the close curly, and the file is gone. So moving things to destroy them is a thing that you might do in Rust. So the fact that all types are movable leads to this idiom being more common in Rust than any equivalent would be in C++. So that was a lot of talking, and now we have a very wordy slide to conclude this section. So at a high level, C++ moving is a special constructor, the move constructor, right? And it can run arbitrary code. And in the Rust case, it's a bitwise destructive move, a destructive bitwise copy. So those are the high level differences. And in practice, that has a lot of consequences for both languages. And it turns out that means that each language is sort of capable of doing some things that the other language can't do, or maybe can't comfortably do. Obviously C++ and Rust, you can do anything, with unsafe code or with, crazy pointer operations maybe, but with, comfortably, idiomatically, the languages have different capabilities because move works differently. And if you'll bear with me, I do actually want to talk about every bullet on this slide. If you aren't much of a C++ programmer, and maybe a lot of this move stuff didn't make a ton of sense, it's okay to skip this slide. But if you're very familiar with how move works in C++, these bullets are a great way to kind of look right at the nitty-gritty differences of how these different move semantics affect the language. So I'm going to talk about each one of these. So starting on the C++ side. So mutex in C++ is an example of a non-movable, immovable type. So it has no move constructor. If you try to call standard move on it and assign it to somewhere else, it's not going to work. It's not going to compile. And that is useful. There's a reason for that in C++. It's not just that they forgot to define a move constructor. It's because mutex may be backed by operating system APIs that cannot tolerate moving the lock to another location in memory. In particular, on Linux, the futex system calls that you make to implement mutex, they use the address of the lock as an argument. So you can't lock something at one address and then move it and try to unlock it at a different address. That's not a valid use of the operating system API. And so mutex doesn't really want to move. And in C++, that's totally fine. It just doesn't have a move constructor. You can't move it, like problem solved. In Rust, well, every type is movable. So here, when in Rust's standard library, there's a mutex type. We've already seen it. And like everything else, it needs to be movable. So the way that Rust solves this is that it makes a heap allocation inside of Mutex on Unix. On Windows, it doesn't have to, I think. But on Unix, it makes a heap allocation. So the Mutex object is actually a box, a unique putter of the operating system Mutex object. So you can move the pointer around and it owns this allocation, and that's fine. And the allocation itself never moves, and so it satisfies the operating system requirements. But that heap allocation is not free, right? So that's an example of the requirement that every type in Rust is mutable. In this case, not in most cases, but in this case, has a cost. It has a cost. It means Mutex has to allocate on Unix. Another example of something that C++ can do that Rust cannot easily do in safe code, is it turns out that we've seen small string optimizations so far already in this talk, and it turns out that the way that the small string optimization is done in GCC's implementation, not in others as far as I'm aware, but in GCC specifically, the small string optimization is self-referential. So what happens is, normally when you do a small string optimization, you have some flag somewhere. So when I want to read the string, I'm going to check this flag and I'm going to say, is it small or is it big? Or maybe I just check the length or whatever. And I have an if statement that knows that if it's above the threshold length, then the string is on the heap, I should dereference this pointer. If it's below, then the characters are stored locally. So that's some sort of branch, some sort of if statement, some sort of check, right? That's the typical small string optimization. GCC's small string optimization is more interesting than that. So what they do is when in the small string case, when they store characters in line, they actually keep the pointer field. Like, they don't store characters over the data pointer. They actually have the data pointer point into the adjacent field of the struct, of the class, that's holding those characters on the stack. They point into that so that when I want to read the string, I can just unconditionally dereference that pointer. I don't have to ask whether it's pointing to the heap or pointing to the stack. It just works. So I save myself a branch. It's an interesting optimization. It's a very interesting optimization. So they have this pointer that points, the struct holds a pointer into itself, into a different part of itself. It's kind of circular. And what that means is that the string in GCC's implementation cannot be bitwise moved. So if you move a string or copy it, but either way, if a string moves to a new location, if it's small, then its data pointer, if you just did a bitwise copy, the data pointer would still be pointing back to the old location. You just copied that pointer. So the move operation on string in GCC must update that pointer to point to the new, self-referential location, right? It's a new place in memory. That pointer has to be updated. That's not a bitwise copy. In C++, that's okay. Totally fine that the move constructor does this. In Rust, you can't have that behavior in safe code. There's no way to tell Rust, oh, when you move this type, run some extra code, call this function, update this member. Like, no. All moves in Rust are bitwise. So Rust cannot implement this optimization for string. Not in safe code. Not if string is going to be available to safe callers, right? Now, it can implement other small string optimizations. It could have. It turns out that it doesn't. But it cannot implement this particular one. So here's a case where C++, in the case of GCC's implementation, is able to make a choice that this choice is not available to Rust. Now, there are many different ways to implement strings. It's not always the best way, but it's a way that is at least the best in some cases. There's a reason GCC chose that. That choice is not available to Rust. So that's a limitation because of the move semantics. So now let's talk about things that the Rust move semantics do to benefit Rust. So those are sort of things that benefit C++, or things that in Rust are costs, things you cannot do. It requires a heap allocation to work around. But in Rust, we benefit from the fact that all types are movable, right? So the first bullet here is a really interesting conceptual leap. Constructors in Rust, we've seen a few of them. In fact, let me go back. Most recently, we saw, for example, here's an example, right? Vec new. That's a direct call to construct a new vector, right? Constructors like this in Rust, they're just regular functions. They're actually not special. So constructors in C++ are quite special, right? They don't return a value. They're called in certain special cases by the compiler. constructors in Rust are just functions. They just return a value. And because everything is movable, you don't need a sort of special in-place construction operation. You just instantiate any type by initializing its fields, and then you return it, and it's just moved out of you, right? So every time you see new in Rust, it's not a keyword, it's just a function. So that's sort of a surprisingly large conceptual difference between the two languages. Like Rust basically doesn't have constructors. It just has functions that return values. So that's dramatically simpler when you think about all the different types of constructors that are available in C++. Nothing like that really exists in Rust. It's just functions. A more specific difference in the same category, because everything is movable. So with mutex, for example, right? Being movable was like a cost. It was like we had to do extra work to meet that requirement. But from the perspective of the container type, so if I'm containing a bunch of values and moving them around, the fact that everything is bitwise movable is a strength. It's like it gives me more capabilities. So in the case of Vec, when I want to do shifting operations like that remove operation, I'm always going to do that with the equivalent of a mem move. So I'm just going to make that compiler intrinsic call that says move this memory over. And even if that's a million elements, right? It's just slide them over, right? And that bitwise memory move is going to be like vectorized by the compiler. It's like it's as efficient as possible according to the platform, right? And C++ is sometimes, but not always, able to make the same optimization. So real quick, I want to look at a case of that. This is another clickable link. If you click on this image in the slides, it will take you to this Godbolt example, and you can play with it. So here, I have a vector of vectors. So I'm taking a vector of vectors. So here, vector, vector, int, a vector of vectors of int, and I'm erasing the first element. So I'm popping out the first vector and deleting it. And in Rust, that's the remove method. Right? I have vec of I32. That's like a vector of vector of ints, and I'm just popping out the first vector and deleting it. Right? In Rust, that's a mem move. It's a mem move because every call to remove will be optimized as a mem move, unless the length of the vector is like a compile time constant, I suppose. But in general, every call to vec.remove is a mem move because everything is movable. That's just always the correct implementation. In C++, you can find this optimization if the element type is, if you have just a vector of int, for example, you will probably see the same optimization. It will probably be a mem move. But in this case, standard vector, the element type is not trivially copyable, right? So C++ is not going to be able to apply the mem move optimization here. It's going to loop over every element of V, and it's going to call the move constructor to move every element down in a loop. It's not going to be a vectorized mem move here. Now, my understanding, again, I'm not a C++ expert. My understanding is there are a number of proposals out there that might extend C++ in the future with some sort of annotation that says that a type is bit copyable or something like that. So it's possible that a future version of C++ will be able to make this optimization in this case. But here with GCC, we don't see it. And that's because the compiler can't just assume that all types are bitwise movable, right? It has to respect whatever the move constructor is doing. Whereas Vec and Rust can assume that. And so Vec optimizations can be more efficient. Another thing that Rust benefits from is the destructive part of destructive bitwise copy. So every move in Rust evaporates the moved from object, right? And what that means is Rust does not need, the moved from object doesn't need to represent the empty state in any way. It doesn't get emptied. It just goes away, right? There is no moved from state. You're just gone, right? And that's not true in C++. In C++, when you move from an object, that object has to be placed in some state that's like conceptually empty, probably, that can be destructed safely, right? And one place that I think that causes trouble is unique putter. So unique putter, that's the uniquely owned heap allocated type in C++. It's a modern type. It's a great type to use if you need to make sure something is movable, and you want to carefully control the lifetime of a heap allocated thing. We don't use new anymore in modern C++, right? We use unique putter and sometimes shared putter. The Rust equivalent is box, and one big difference between unique putter and box is that unique putter is nullable. So unique putter has a default constructor. It can be null. And if you move from a unique putter, it will null out the source. So in general, if someone calls you and gives you a unique putter, you might need to be defensive about the fact that, as with any other pointer, like that unique putter might contain a null pointer, right? And it would probably have been nicer if that wasn't true, right? Like references in C++ are not nullable, right? You can only create a reference by pointing to a valid object, right? That's nice, right? We often like that. It makes our code less error prone, less confusing. But unique putter can't achieve that behavior if it wanted to, because it has to have a moved from state. You have to be able to move from unique putter and leave it in some state. And so that's one way or another, that's basically the null state. So that's a limitation in C++ that Rust doesn't have, because Rust moves are always destructive. So this has been a somewhat exhausting collection of specific differences between the two. This slide is aimed more at people who are very familiar with move in C++. So if you have skipped over this slide, that's okay. We're about to move to the final section where we put everything together. Arc mutex string. So we've previously seen some examples of multithreading. So we saw the for each loop, right? And that's a very kind of carefully controlled type of multithreading, right? The threads are owned by some global thread pool, and our closure runs on them, and then once for each returns, right, we don't see those threads again, right? But of course, it is also possible to do threads the old-fashioned way, where we spawn our own background threads that run who knows how long, right? And when we do threading that way, we need to use all the tools that we've kind of seen so far to make it work, because Rust is going to be very careful with us. Rust was not going to compile our code unless it is sure that our threading code is not causing any memory safety issues, right? And that can require quite a lot of doing. So we're going to see here in this final section an example of free-form multithreading, right? Our own threads that run until we join them, and do whatever we said to do. Maybe run forever. In this case, we're going to join them, but we don't have to. We're going to see how to make that work in Rust. So here is a complicated example. And we're going to talk through this very carefully, right? Because it's doing quite a lot. We're going to go line by line through C++ here. Small spoiler alert, this Rust code is not going to compile here. On the next slide, we'll see the version that compiles. On this slide, it doesn't compile, but it almost compiles, if there is such a thing. It's very close to compiling. And so I think we can still talk about it line by line and get some good ideas of what's going on. So C++, what are we doing? Right, we're creating a string, which we're going to mutate from 10 different threads. Right, creating a mutex is going to lock that string, and then we're running a loop spawning 10 threads. Right, so each of these thread handles is going to get pushed in this vector of thread handles so that we can join them, and each thread is spawned to run this lambda. Right, so this is capture by reference. So what that means is this reference to my mutex, this reference to my string, those are implicit references that will go in each lambda. We're using the lock guard. We saw that before, right? That's familiar standard C++ lock guard. And then with the lock held, right? The lock guard takes the lock. We are mutating the string. We're appending some characters to it, right? So 10 threads are doing this. And then once those 10 threads have been spawned, we will loop over the vector of handles and we will join each of the threads. So once this join loop is complete, we know that all those threads have returned and we've appended some characters to our string 10 times, right? So this code is, I'm going to say this code is 99% correct. You can compile this code, you can run this code, it will do what it says it does. Thread sanitizer will not complain. It's not a data race. Typically, 99% correct. It's definitely not a data race. I'll say that much. The Rust code is doing the same thing. So we saw this before. Mutex is a container in Rust. So instead of having my string and my mutex on the left, I'm just calling it my string, but it's a mutex of string. It's a mutex that contains a string. And we can see this constructor here. Remember that new is just a function that returns a new object, right? It's the constructors are not special. They just take objects and return them. But mutex new of string new. So this is a mutex that contains the empty string. And then we loop 10 times and we spawn 10 threads and we put them in the vector just like we did over here, and we join them just like we did over here. So a lot of this is the same. You may remember from the previous example, the mutex guard, which we create here, is a smart pointer. So we actually go through the guard. The dot operator here implicitly dereferences the guard, gives us a reference to the string on which we call the push stir method. So push stir is how you append characters to a string. So this is going to get called 10 times. So this code is trying to do the same thing. Now, I said this code is not going to compile in Rust. That's true. So if you try to compile this code, Rust will complain. And Rust will say, closure may outlive current function. So, but it borrows my string, right? So what is Rust worried about? Well, these closures are implicitly, sort of as in C++, they're implicitly taking a reference to a local variable, right? We have this myString variable, and we can see that that's referenced inside the closure, inside the lambda. And what Rust is worried about is this pointer, this implicit pointer that this closure is going to get created with might dangle. So for example, if the calling function were to return somehow before doing all the joins, then its local variable, myString, would be destroyed, right? So if any of these threads were still running when the main function, the calling function returned, that would be really bad, right? That would be a dangling pointer. That would be an invalid reference. So totally break the rules. Use after free, right? So Rust is worried about that. Now, we know, that our code is not going to do that because we know that join is going to wait for all these threads to finish, right? So we know that it's not going to happen. But Rust doesn't really know that. So, the fact that we stuff these thread handles in a vector and that we loop over that entire vector and join each one, it's not really visible to the Rust type system. It's sort of like a runtime fact of our program. And Rust doesn't really follow that in any way that it can prove things about. So Rust is scared about this. It's sort of, Rust effectively doesn't see the join loop, right? I want to point out before we move on that Rust does have a point here. If I go back, we might ask, what does this code do if, for example, the creation of a thread happens to throw? Which it could do, right? You're spawning a thread, like that operation can fail. That can totally throw an exception. What would this code do if spawning a thread threw an exception? Well, it would exit out of the current function. So the join loop would never be executed, actually, and it would destroy these locals on the way out. So that might actually be quite bad here. And this is part of why I said 99%. So if creating a new thread were to throw, we're actually not joining these threads. Now, it turns out that C++ is a little bit cautious here and kind of has our back. So when standard thread is destroyed, if it hasn't been joined, it will call standard terminate. So it'll just quit your entire program. If you allow a thread handle, a standard thread, to be destructed without having joined it and without having called the detach method, I think, it will terminate your entire program. Because it's worried about this problem, right? I mean, it's sort of presuming that if you exited early with some exception, you probably haven't joined these threads. They're probably accessing locals, right? Like, that's really bad, right? It's being defensive about this problem. So in this case, we can reason, okay, we initialize the variables in this order, string, mutex, vector of thread. That means they're destructed in the opposite order. So the vector of thread handles is destructed first. So that means if we didn't join them, we will terminate the program before destructing my string. So good, I guess, right? Like, so like that's good. When we wrote this code, I'm not sure we were paying extremely careful attention to the order of these variables, right? So the fact is that if I had declared my string after this vector, then my program would actually be doing a use after free here, right? The threads could actually access the destructed string in that tiny window before state or terminate ended up getting called, right? We would have memory on safety if we had declared these variables in a different order. That might be very surprising. This code can also terminate our program, which is perhaps surprising. We may not have intended to allow this function to terminate our entire program, but it can. So that's why I say 99% here. So this code generally does what you think it does. It is memory safe, but that safety kind of hinges by a thread, if I'm allowed to make a terrible pun. That safety is much more precarious than it might look at first blush. So I think Rust is being reasonable when it complains about this code. It has the same problem. The thread spawn in Rust can panic, right? And Rust does not have the defensive measure that C++ has. A Rust thread will not terminate your entire program if it's destructed without joining. It'll background. It'll detach the thread. So Rust is actually quite right to complain here, right? If we wind up with a panic inside a thread spawn, we have a problem. So the next slide is about solving that problem. Real quick before we get there, though, we might remember that the for each loop in the previous section was perfectly happy to reference our sum atomic, but also the sum mutex, right? That shared sum integer, right? That works just fine. But here, thread spawn doesn't want to reference stack locals. How does Rust know about that difference, right? Previously, we saw that the different types of for each loops have different trait bounds. That's true here as well. The bodies don't matter, right? And, we're not going to talk about what exactly send and sync mean, but we can notice that the spawn function has a static lifetime bound on the closure that you give it. So this is how Rust knows. So the spawn function has said, hey, I know I can't guarantee that this thread is ever going to terminate at any particular time. So I'm going to demand that this closure that I'm going to call on this thread doesn't have any references to anything of limited lifetime, because I cannot make any static guarantees about abiding by those lifetime constraints. This thread's just going to go, and it's up to the runtime behavior of the caller to join it if it wants to. And I can't necessarily prove things about that. So that's what this bound means. Again, the exact syntax is not important. What's important is we can see that these functions are being explicit about their safety requirements. That's how Rust knows what you're allowed to do with them. That's what makes these interfaces sound and safe. Even though, of course, spawning threads on the inside is some system call, right? It's probably some C standard library function. Who knows what it does? But we can wrap it in safe interfaces. This is how sort of everything works under the covers. Each function says its requirements and its signature. So now, I said we can make this code compile. We can make it compile. So here we go. This is mostly the same as in the previous. Oops. This is mostly the same. What has changed? I have put the mutex in the string inside a shared putter. So a shared putter, that's the heap allocated reference counted pointer in C++, right? So as long as you have any copy of the shared putter alive, it keeps the object on the heap alive. So then what have I done? I have made my closure, instead of capturing by reference, it's now capturing by value. In C++, that means that the shared putter is copied. Its copy constructor runs. And so that's going to increment the reference count for every thread, right? And now, because mutex in C++ is not a container, I use a pair of mutex and string. So the shared putter has this pair inside of it. So that means that I have to access it through the first and second sort of member variables. But it's effectively doing the same thing, right? It's locking the mutex, it's mutating the string, and this by value copy means that the reference count was incremented. And so this shared putter will definitely not be freed until all these threads have returned, right? So that's what's changed. On the Rust side of things, shared putter is called arc. So this was the subheading of this section, arc mutex string, right? So here we see this string of constructors, which again, new is not a keyword. These are just functions that return new objects. And we have an arc of a mutex of a string. So we have put a string inside of a mutex, and we have put that mutex inside of an arc. So it's allocated on the heap, and there's going to be some sort of reference counted access to it. Sort of like we changed the lambda over here to be a by value, by copy capture. In Rust, we've added the move keyword, which makes this lambda implicitly move in every variable that you have referenced. So it's not going to hold any implicit pointers, the color stack. It's actually going to move those values in. Obviously, we cannot move my string more than once. And so in order to, if we tried to move it more than once, like in this loop, our code would not compile. So instead, we make a local variable that's a clone of it. Remember, when in C++ we do things that would invoke the copy constructor. In Rust, we use the explicit clone method to get the same behavior effectively. That's true here as well. So we've incremented the reference count of my string, the arc, the atomic reference counted pointer, the shared pointer. We've incremented its reference count and made a clone into this local variable. We then move that clone into the lambda by referencing it. So when we say our clone.lock, we're calling lock on the mutex through the arc, which is a smart pointer, right? We're getting the lock guard, and we're using the lock guard like we were doing before. Right, so these two pieces of code are doing the same thing. In C++, it's a pair. In Rust, the mutex is a container and the guard is a smart pointer, but they are doing the same thing. These two pieces of code both compile, both run, they're both correct in both languages. So this is how you do it. So we can stare at this. This is a lot, right? Like this is not simple code. And like this, code like this is one of the reasons why Rust has a bit of a learning curve, right? You really have to familiarize yourself with all these library types before you can get anything like this to compile, right? And, for new Rust coders, that can be pretty frustrating. That's true. But, in C++, it may be easier to get things to compile, but we saw, like in the previous example back here, these locals can have maybe some confusing, surprising memory safety issues. It's surprisingly difficult to write memory safe code in C++ in cases like this. So the fact that Rust won't compile our memory safety mistakes, it's a hurdle that the new programmers have to jump over very early, but it's a hurdle that they probably want to be jumping over. And, forcing them to confront that hurdle has benefits as well as drawbacks. So I want to continue this section and get to my favorite example and the sort of concluding example in this slide, in this whole presentation, by talking about more ways that we could have gotten this code wrong and how Rust catches those mistakes. So here's an easy one, right? What have I done in this case? It's the same code as before. It's got that shared pointer on both sides, but look, what have I done? I've forgotten the lock. Right? Actually, I haven't totally forgotten it. I did create the lock over here in C++. It's in the pair, but I just omitted the line with the lock guard, right? In this case, I've written the same code in C++, but I just didn't take the lock. Just forgot, right? So in C++, this code is just totally unsynchronized. So this is like a horrible memory safety issue, right? So if you run this code under tsan, it'll tell you this is a data race. And it may or may not crash, because it's also probably going to be a use after free, as that string keeps reallocating its storage, right? So this is a data race, right? This is a totally unsynchronized piece of code. You just have to be careful, never to forget to take the lock, right? The Rust code, now obviously because the mutex guard is a smart pointer, we can't really syntactically express forgetting to lock the mutex. We wouldn't have the pointer, but we can do the next best thing. So here we've just left out the mutex entirely. So we've arc new of string new. There's mutex new is gone. And we're just trying to dereference the arc directly. So we're going straight through the shared pointer. There's no mutex. We're not trying to take one. And in Rust, this is a compiler error. It turns out that this compiler error is basically a simple type error. So there's no fancy lifetime issues or anything like that here. What it's saying is cannot borrow data in arc is mutable. Like arc knows that it's a shared pointer, right? That's its whole purpose for existing, is to alias some value in the heap. That's why you use arc, right? And so arc it knows it can't give out mutable references because it would violate the aliasing rule if it did that. It would have no way to protect the aliasing rule. And so it just doesn't implement that operation. So the deref operation that returns a non-const, a mutable reference, arc just doesn't implement that. It doesn't have that operator. So this compiler is effectively saying this operator doesn't exist. Rust refers to it as the deref mute trait. And again, we're not really talking about the details of traits, but arc knows it can't support this operation. This is a simple type error. It doesn't compile. Look at another version of the same. So what have I done here? Here I've switched from mutex to shared mutex. And in Rust, I've switched from mutex to RW lock. So what's a shared mutex? What's a read-write lock? It's a lock that can allow any number of readers at the same time. So multiple reading threads can take a read lock simultaneously, but you can't have any readers at the same time as you have a writer, and only one thread can take a write lock. So it makes the writer exclusive to any readers, but the readers are not exclusive to each other. That's a read-write lock. By the way, pretty similar to Rust's rules about references, right? A read-write lock in both languages, a shared mutex, is kind of like, the Rust references, right? If you want the writable one, the mutable one, there can only be one, right, at a time. So what I've done here, I'm using this shared mutex, but oops, I took the wrong kind of lock. So a shared lock guard that's the read lock. I've taken the read lock here, not the write lock. You can see in Rust, RW lock, instead of having the lock method like mutex does, it has a read method and a write method that take a read lock or a write lock. And here I've called the read method. So I've made the same mistake. I should have taken a write lock here because I'm about to mutate the string, but I took the read lock, oops, right? And in C++, what that means is it's sort of like forgetting to take the lock at all. Like this code is just totally unsynchronized, right? I'm doing mutation without having taken an exclusive lock, TSAN, right? So it's a TSAN failure. In Rust, it's a compiler error, and it's very similar to the previous example. So arc, it just sort of knows that it's not supposed to give out mutable references, right? It just doesn't implement that operation. The RW lock read guard is the same. So the type of lock guard returned by the read method is different from the type returned by the write method. And the read guard here, doesn't implement deref mute, right? It doesn't implement that operation where you get a mutable reference out of it because it knows it's not supposed to, right? It's the read guard, right? Like it's not supposed to implement that operation. So this is, again, kind of a simple type error in the Rust cases. Like it doesn't have this method, basically. This code just can't compile. It's trying to use an operation that doesn't exist. If you're interested, this fabulous talk by Louis Brandy from Facebook, where he talks about a bunch of different bugs, but one of them is basically this bug, and he goes into a very surprising example of C++ syntax where you can think you're taking a lock guard and fail to, and you're actually not locking anything at all. This is another clickable link. If you have time, click on this, and it goes to the right time in the video, and listen to this part of the talk. It's fascinating, little C++ minutia of what the standard will parse. There's no Rust equivalent of this particular bug, but if you want to click through, I highly recommend actually watching this entire talk if you can, or at least just the part that this link goes to. It's another example of the same. It's just fancier and more obscure ways to just forget to take a lock. But I want to move on to here, the very final example in this entire talk. So this slide is what we've been building up to the whole time. So we've got everything here, right? We've got moving, we've got references, we're going to see some lifetimes. So what are we doing? Here, let me highlight the relevant code. We're using a mutex, we're using a lock guard, so we haven't forgotten to lock, and we haven't accidentally taken a read lock. We've gone back to the regular thing, lock guard of mutex, right? We're definitely taking a lock, and we're taking a pointer to that string in the critical section, while we have the lock, right? But what's our mistake here, right? We're smuggling that pointer out. We're sort of placing it in some longer-lived location, and then by the time we actually get around to using that pointer, we've left the critical section, right? This closed curly, the lock guard has been destroyed. We're not locking it anymore, so this is unsynchronized. So obviously this is an example just for a slide. How would this happen in the real world? You'd probably call some method on some object and you'd give it a reference to the string, and maybe you don't realize that the method is taking a copy. It's like stashing that reference somewhere in some field that you don't know about. And then later outside of the critical section, you call another method that uses the stashed string. That's probably how this would happen in the real world. Here I'm just doing it with curly braces so that we can see it. But so it's like we came into the critical section with the best of intentions, right? We took the lock, we accessed this shared value with the lock held, but we didn't leave the critical section, cleanly, right? We retained some references as we left, and then we used those references later, but we're not supposed to do that. Like, that's the mistake here. The equivalent code in Rust will not compile. And I think it's very interesting that in the previous slides, the mistake was either a simple type error, like is an operation not implemented, or maybe it wasn't even syntactically possible. Like if you try not to lock the mutex, you don't get your smart pointer. So you can't really express like totally forgetting to lock the mutex if it's there. But this code is totally valid, like syntactically, right? It's expressing an operation that makes total sense, right? We're creating the guard. We're getting a pointer to the string it contains. Right? We've dereferenced the guard and taken a mutable reference to that memory location. You are allowed to do this. Line 8 is valid. We try to leave the critical section by destroying the guard. I could have used the curly braces here also. I could have written it the same way, and here we use drop because it's Rust. That's pretty convenient. And then we try to use our smuggled reference after we've left the critical section, after the lock has been unlocked. And Rust catches this. So what is this? Cannot move out of guard because it is borrowed, right? We saw this when we were talking about big idea number 3, right? How to move semantics work. When you move an object, if it has outstanding references, you can't do that, right? You're evaporating the object, but you've got a reference to it. Like that's not safe. Your code will compile. Same error here. If we had written this with the curly braces, we would have gotten the same error as on like the very first slide, the very first example, like my int equals 5, right? Like you have a borrow that is outliving the thing that it's borrowing. Like one way or another, no matter how we try to do this, like this cannot compile. It cannot compile because Rust knows that this pointer that we have taken to the string borrows the guard. It must not outlive the point where the guard is destroyed. So this is my favorite slide in the entire talk. This is what we were building up to, right? Because this is where Rust guarantees that not only do we enter the critical section correctly and cleanly, but we leave it cleanly too. We don't retain borrows that we're not supposed to retain. I think it's very interesting to ask, this model where the mutex is a container, right? You contain the object that you lock. That's pretty cool. That's like a pretty good idea. Why don't other languages do that? And other languages totally could do that, right? C++ could define a mutex that was a container. That's a generic type, totally doable. But languages other than Rust really cannot catch this mistake. So if, imagine I had a mutex container in Python, right? It has some accessor method that returns a smart pointer, and maybe I use it with a with block or something, somehow guarantee that it's limited in scope. But once it gives me a reference to that contained object, there's no way for like a Python or C++, container mutex to kind of claw that back, right? There's no way for it to prove or help me prove, sort of force me not to retain that reference. Once I've got it, it's just a pointer, right? So to get that kind of ironclad guarantee that you're not racing against this object, you're only using these references inside the critical section, you need lifetime tracking. And that's kind of why I like this example so much, because lifetimes borrowing, these notions, they're invented for memory safety, right? Like they're the first job of the borrow checker in the compiler, right? The lifetime system is to make sure that I don't use some pointer to an object that's been destroyed. I don't use after free, right? That's like, 80%, 90% of the job of the lifetime system. But here we see an example of the mutex type expressing a much higher level invariant through the borrowing, ownership, and lifetime mechanisms, right? The mutex is expressing the invariant, like you must not access this contained object except in the critical section where you hold the lock, right? And we're enforcing that with the borrow checker, right? The reference rules guarantee that that's correct. So we're leveraging this lowish level notion of lifetimes for a much higher level guarantee. Rust, the language Rust doesn't know anything about mutex, right? Mutex is some library type. It makes some system calls. Like, who knows what it does? Like Rust doesn't even really know what a thread is, really. But it doesn't matter because the mutex, the library code that implements mutex, is able to express the invariants that it demands through the type system, through the lifetime rules. And we're able to achieve this ironclad guarantee about this code, right? Like what we're doing is super complicated, right? We spawn 10 threads. We've got this arc, this shared putter that's aliasing across all these different threads. And, but we're able to kind of like all that complexity kind of melts away, as I've done in this slide, right, with the font color, right? That complexity melts away, and Rust is able to just see this in terms of a borrow that's going out of scope, about an object that's being moved. Simple rules in this very complicated context are able to express the guarantees that we need. So that's why I think this is like the most exciting slide in the entire talk. Like this is really like ad hoc threading, with aliased mutexes and stuff. Like we can write this code, and when we do, Rust can check our work. And the guarantees with no seg faults, no use after free, no data races, right? No races to mutate shared values. Those guarantees are upheld here in this very complicated case. So I think this is very exciting. I think this is sort of a great sort of keystone or example of the Rust borrow checker in action. And so I'll leave us here. Thank you for listening to this very long version of the talk. And if you made it through this one, feel free to check out the faster version that I'm going to record next.